Welcome. It's time to talk about vector functions. And this is where the calculus part of this calculus class really begins. So, we have talked about vectors as related to points. This next chapter, we really get into the idea of motion in space. So, this is the basis of rocket science, if you will. Literally, if you've got a rocket in space, you can have a vector pointing to where it is, but then there'd be a velocity vector pointing in the direction it's moving. And of course, that velocity vector is always changing. So, what does this mean mathematically? Well, we have a definition of derivative back from Calculus 1. And again, all we do in this class is add a steering wheel to the calculus we already know. So, the velocity vector is the derivative of the position vector. And so we have the same form as we had in Calc 1. The limit, in Calc 1 they used h. I don't want to use h because it's taken later. So we'll just say delta t goes to 0 of r of t plus delta t minus r of t over delta t. So let's look at what that looks like in practice. Let's take a really simple example. Say a parabola. So the straightforward parabola of y equals x squared. Now we don't usually like to do that. We usually like to parameterize it. So we'll say t is x and y is t squared. So r of t is t squared. And now, let's see what that would give us. So, let's take the point 0. So here's t equals 0. And then we'll say t plus delta t. So, t plus delta t can be over here. Now, the difference quotient was r of t plus delta t minus r of t all over delta t. So we would take the straight line vector between this point and this other point. And then we would divide it by the amount of time that passed. Meaning the length of the vector is essentially how fast we are moving along this curve. If we took a closer point, a smaller delta t, it gets flatter. Take a smaller delta t, it gets flatter. As delta t goes to 0, this vector will become horizontal. It will become the tangent vector. So the limit delta t goes to 0 of this is, we call it v for velocity, and it is the tangent vector. So, for any other example, let's say I have curve like this. It's going in this direction. If I pick this point here and I tried to work out what the tangent vector was, what the velocity vector was, it would be like this. If I pick this point here and I work out the derivative, it would be a vector like this. If I picked a point here, the velocity or tangent vector, the velocity vector would be tangent like that. So, just like in Calc 1, if we take a derivative and plug in a point, we get a vector that is tangent to the curve that we're looking at. So, this is where I really want to just conceptually, what you're thinking is r is position. So that's where we are. And v is velocity, where we're going. And you can probably guess that acceleration is coming up in a little while, but we're not going to get there just yet. But I want to make one quick definition here, and it should be in the notes later, but if it's not, let's say it now. Absolute value of v is called speed. Velocity is a vector, speed is a scalar. And so the idea being that a lot of times we want to analyze curves based on how they're... That one doesn't look right at all, does it? Based on which way the velocity vectors are changing. It shouldn't matter whether the velocity vector is longer. That's really not a statement about the curve itself. So, absolute value of v is speed. Keep that in mind. And what we want to avoid is any idea that how fast you run along the curve has anything to do with its shape. So oftentimes we're going to want the speed to be 1. But let's not do that just yet. Let's start off with an example of how do we actually do this. Well, we said in the last unit that limits distribute to each component. Now, because everything about derivative is based on limit, derivative also distributes. So if you've got a vector function r and you want to take its derivative, you just take the derivative of each of the 3 components with respect to t. And so that does work out exactly as you'd like it to. So let's do an example. Find the derivative of r of t is t squared I minus 4j. Okay, t squared I minus 4j. Well, then the r prime would be 2ti plus 0j. Because derivative of 4, it's a constant. What does this represent? Well, let's think this through. We've got r of t is t squared I minus 4j. So r of r of 0 is negative 4j. R of 1 is 1i minus 4j. R of 2 is 4i minus 4j. What would we put in r of negative 1? Well, that would give us also 1i minus 4j. And so what this is then, if we have a xy plane here, we have the line here, y equals negative 4. And what we are seeing then is the position would go this way, and then it would turn back. Or the points would go that way and turn back. So the position vectors would be here's 1, and then here, and straight down, and then back the way they came. The velocity is always change in position over time, so they would be horizontal vectors. R prime is 2ti, but with no y component, because the change is always left and right. Now we can also do this in our graphing software. T squared I minus 4j. So if I go over here, I'm going to say let's add a space curve. These are called space curves. I said that. We'll turn off this other thing. And we'll put it in 2D because there's no z component. And so we'll have t squared for I and negative 4 for j. And put 0 for t. Okay. This does, in fact, what we were saying earlier. Let's zoom out the y so we can see the whole thing. Can we zoom this out a little? There's the 4 down there. So if I push trace, let's plug in a value for t, like 1. And it shows where it's pointed. And this second arrow is, in fact, the velocity. Plug in t equals -2. And you push animate and watch it move as time goes by. Oh, there's 2 arrows. I think one is velocity and one's acceleration. Okay, so since it's moving left one, this black one is the velocity. And you just put in a specific time if you want. Time 3. So it's pointing outwards because when t is positive, it's moving back to the right. We put in time -3. Same position, but now it's moving to the left. So yeah, this is something I want you to play around with. I think it will help you understand things. That said, I don't want to do it for absolutely every problem. It would take too long. All right, let's find the first and second derivatives of this function. 1 over ti plus ln of tj plus e to the 2tk. All right, here my paper's rustling, so I don't have to keep switching back and forth. Clear this. All right, r of t is 1 over ti plus ln of tj. If I ever say log, I mean natural log. It's the only log we use in this course. Okay, so the first derivative, r of t, would be -1 over t squared I plus 1 over tj plus 2e to the 2tk. That's r prime, which is also v of t. Then r double prime of t would be, let's see, -t to the -2. So the derivative would be 2t to the -3. So 2 over t to the 3rd I minus 1 over t squared j plus 4e to the 2tk. And while we're at it, why not just do a test point? Why not, let's try 1. R of 1 is 1i plus 0j plus 1k, or plus ek. R prime of 1 would be -1i plus 1j plus 2ek. And R double prime of 1 would be 2 I minus 1j plus 4e, which should be a squared, shouldn't it? E squared k. E squared k. So let's graph this one. I want to see it's a 3D, so I'll have to switch to 3D mode. And so let's type this in here. It's 1 over ti, and for j it's ln of t. For k it's e to the 2t. I'm not sure that's working. I think I did something wrong. Let's skip that one. Oh, there it is. I had to turn it off and turn it back on. All right, so the pale blue line is our space curve. So if we pick a point like 1, and we can see I guess those are the powers of E there. 7.39 or 14.76. But we can see here the blue represents the space with the dark blue pointing at it. And we've got these other vectors showing velocity and position. If I do the animate thing, I can see as it goes. It'll come in quick here. Yeah. If we want to slow it down, we could say -1 to 1, but still 500 steps, so it'll take lots of time going there. You can see the black curve is always pointing in the direction of the motion, or the black vector, I mean. 0.25 to... Depends on how much you want to zoom in. Maybe that's too small. All right, so I encourage you to play around with this and just see how it works. All right, so now that we've done some examples, I mentioned earlier that I don't like the speed changing. The idea being that we want to have statements about the curve itself, so how fast you run along the curve should not matter. So we like to use the unit tangent vector. So here's speed, we said, the absolute value of the velocity vector, absolute value of r prime. So we define the unit tangent vector, capital T, is r prime of t over absolute value of r prime of t. Most likely the quiz on Monday will say find the unit tangent of some function. So let's do some examples. Find unit tangent vector of 1 plus t cubed I plus te to negative tj plus sine of 2tk at t equals 0. All right. So we have r of t equals 1 plus t cubed I plus te to the minus t j, ugly t, plus sine of 2t k. So let's find the derivative here. R prime of t is 3t squared. This second one we need to use product rule. So it'd be derivative of the first times the second, that's e to the minus t, plus the first times derivative of the second, which would be negative e to the negative t. And then the third component would be 2 cosine of 2t. This is a mix of chain rule for the k component and product rule for the j. Again, come by the calc table if you want to review these rules. Now, we could go ahead and plug in the formula. T of t is r prime of t. I keep forgetting to write the prime. Over absolute value of r prime of t. And we could go ahead and do the absolute value formula, which is square each one of these, add them, take the square root. But we were only asked for t equals 0. So let's make this easier. Let's go ahead and plug in t at time 0. And the rule with this is, with any calculus thing really, when you're plugging in to a derivative, is you can plug in as soon as you've taken the derivative. You can't plug in before because there'll be a constant and derivative will be automatically 0. But as soon as you've done the derivative, you're free to plug in whatever value you want, even if you haven't simplified the expression. All right, so that's good. So what is the length of r prime of 0? Well, it is square root of 0 squared plus 1 squared plus 2 squared is root 5. So the tangent vector at time 0 would be 1 over root 5, 0, 1, 2. Or if you prefer, 0, 1 over root 5, 2 over root 5. I would accept either one of these as correct. So this is just the rule we had earlier on about how to find unit vectors, but applied to this specific vector that is the derivative. All right, let's go on to the next problem. Velocity vector. It says, sketch both position and velocity vectors at t equals 1. Root ti plus 2 minus tj. Okay. Now we could deparameterize this. If you want to get an idea of what the shape is, it would be square root of t equals x. So t is x squared. And then y is 2 minus x squared. So in fact, we know what the general shape is already. It's going to be a downward facing parabola. And since we're defining t is, or root t is x, this should probably say t has to be greater than or equal to 0, because otherwise we're taking derivative of negative, so we should probably only deal with the, from here on down. Yeah, the way it's defined, we have root t, so t would have to be greater than or equal to 0, or else it would be undefined. If there was ever a question on a test that you were wondering about that, and it didn't say, like, t greater than or equal to 0, you can always just ask, and I would explain it. So anyway, let's focus on the r. Let's use it with the space curve formula. All right, so r prime would be 1/2 t to the negative 1/2, comma, negative 1. Now we're asked at t equals 1, so we'll go r, it says position and velocity vector. So r of 1 would be, plug in here, 1 squared, 1 to the 1/2 and 2 minus 1. So 1, 1. So this is our position. Our position vector is 1, 1. And it's going to have to point to a spot on the curve. It could never be off the curve because the position vector is how the curve was defined in the first place. R prime of 1 is, plug in 1 here, t to negative 1/2, 1 to negative 1/2, it's 1/2, comma, negative 1. So we're always going to want to base our velocity vector at the same point as the position vector. You know, it's not a rule. We said velocity vectors or vectors can, it's equivalent for any starting point, but it makes the most sense for it to be laying on the curve. So it'll go 1/2 to the right, 1 down. Maybe it's not as tangent as it would look, probably because I didn't draw this quite to scale. Let's see if we can draw this a little more to scale. 1, 2, 1, 2. So we'll go through 2. If I plug in x is 0, if x is 0, y is 2. If x is root 2, y is 0. So it would look kind of like this. And so, I'm bad at drawing. Something like that. If you gave me this on a test, I would give you full credit because, well, I would need to label this. This is v of 1 or r prime of 1, equally good. And this is r of 1. This is a good time to use our software, though. Let's do another curve here. Put in 2D mode. So x is square root of t. Y is 2 minus t. And z is 0. I think this thing will not like it if we don't tell it to make z 0. Let's go ahead and graph this. Turn off the trace here. It's supposed to be a curve. Where's the curve? Let me try this again. X is square root t. Y is 2 minus t. Z is 0. And t, yeah, we got to give it a range for t. Let's say t goes from 0 to 3. And let's put it on there. Okay. And now we were asked at the point 1, so let's type in for trace t equals 1. And there, it gives us the position vector and the velocity vector, which is lying tangent to it. And the little green acceleration vector, again, we'll talk about that next time. We can animate if we want and see how the black vector is always tangent. Okay. So, sketching is something we do a lot of in here. But hopefully it won't be too hard. Now let's say I want you to find a tangent line. Well, if you remember we've talked about with the equation of line, there's always two things you need. You need a velocity vector and a starting point. Well, they give us a starting point. 0, 1, pi halves. So we just need the velocity vector. All right. So our curve is defined by x is 2 cosine of t, y is sine t, z is t. This is sort of an elliptical spiral. We're not going to have to graph it. Derivative. R prime of t, we would have x prime is negative 2 sine t, y prime is cosine t, z prime is 1. So the tangent line, well, the equation of a line is always r of t is r naught plus vt. So r naught is our starting point written as a vector, 0, 1, pi halves. Plus vt, which should be, okay. What is v, actually? V is supposed to be a constant, right? This is something to think about. I will see people do this all the time. They'll write in this whole ugly, complicated thing for V, like this entire expression here. That makes no sense. V is always constant because it's a line. When we're talking about finding the equation of a line, V has to be constant. Be careful with the word always, but for a line, V is constant. So therefore, this is not sufficient. We need to plug it in. So here's the question then. What is t when at the point 0, 1, pi halves? Well, that's a position. So if we look at our position vector, that means 2 cosine t equals 0, sine t equals 1, and t equals pi halves. Oh, well, there we go. T is pi halves. So, let me try and explain this a little better here. R of t equals r naught plus vt. V has to be a constant because it is defining a line. V is changing on this curve, but the line it's not changing on. So, at t equals pi halves, what is the velocity vector? Well, r prime of pi halves is -2 sine pi halves cosine of pi halves 1. Sine of pi halves is 1, so it's -2, 0, 1. So that's my velocity, -2, 0, 1. Right, so r of t, or let's call it something else. Let's not call it r here. Let's call it s of t. S of t is the starting point, 0, 1 pi halves, plus velocity, -2, 0, 1 t. I want to illustrate what this means. I think I really do need to graph this one, so let's go do that. So, we're in 3D. Turn this off. Let's graph. X is 2 cosine of t. Y is sine of t. And z is t. I'll turn off the trace. Oh, I misspelled cosine. There it is. It's a spiral kind of going up like that. Let's let t go up to, say, 10. So you can see it goes up a little farther. And now let's look at the equation of the line that we're interested in. What did we say the line was? Was this? Let's combine the terms so we can have it in a nice vector form. It's 0 minus 2t, 1 plus 0t, pi halves plus 1t is -2t, 1 t plus pi over 2. 2t, 1 t plus pi over 2. So -2t, 1 t plus pi over 2. And if we did this right, where is it? And let's let the t go from 0 to 10, say. Where is it? There's the line. You can see it's a tangent line right there on the curve. If we let t be negative, it goes both ways. So what we are saying is that on this first curve, the velocity is changing. But if we stop right here, the velocity vector is going to point in the same direction as the tangent line. And so what we do is we say, well, we find an expression, a function for velocity, and then we plug in the one point we're interested in, and that gives us our v. So, yeah, that was probably more than I needed to show, or maybe not. But the main point, as always, is velocity for a line has to be constant. All right. So I'm going to go through the next bit a little quicker. Rules for derivatives. These should be very familiar. They are basically the same rules from Calc 1. So here's the sum rule. If you got a sum and take a derivative, you can do each one separately. The constant, a constant c or scalar multiple can be pulled out of a derivative. These first two together is called being a linear operator. You can split a sum and you can also pull out scalars. Product rule here. if it's a scalar function times a vector function, you can use product rule, same as in regular one variable. Same with both dot product and cross product. They both have the same product rule. And the chain rule. If we have vector function with a scalar function inside it, you can do u prime of f of t times f prime of t. The other way wouldn't work. It would get you a meaningless expression, but this way works just like you'd expect. All right, so there's a couple more things. Orthogonal velocity. Here's a theorem. If r of t is constant distance, then r dot r prime of t is 0. So velocity and position are going to be perpendicular. Why is that? Well, we have r of t is c. So absolute value of r of t is always a c. And that means we're on a circle, because it's saying the distance from the origin is always the same thing. Well, this is also the same as saying r dot r is constant. And so if we do derivative of both sides, we do product rule. Remember, because this is square root of r dot r. So if it's constant, then its square is also constant. So we get r prime dot r plus r dot r prime is derivative constant 0. So 2r dot r prime is 0, which means r dot r prime is 0. So r and r prime are at right angle to each other. So on a circle, the velocity is always perpendicular to the position. Cosine of t plus sine of t. R of t is cosine ti plus sine tj. R prime of t is negative sine ti plus cosine tj. The dot product between them would be negative cosine of t sine t plus cosine of t sine t. And of course, you can look at this visually. You can say, let's do a 2D plot. Okay, right. This one is said as an ellipse, but let's make it a circle. And if we do the animation thing, you can see the position and the velocity. Oh, turn that off. The position and velocity are at a right angle to each other all the time. So this is a really meaningful idea for talking about orbit. When you're orbiting a satellite that orbits, it's going to always be moving tangent to its orbit. Okay, last thing is antiderivative. And this is, again, just what you would expect. We're not really talking about integrals in the sense of like area and volume right now. We're just talking about it as in we have a function. We want to find some thing that is its antiderivative. So let's find the indefinite integral and then find the definite integral from 0 to pi halves. So again, it's just what you would expect. We just go component by component. So r of t is 2 cosine ti plus sine tj plus 2tk. So the antiderivative r of t dt would be, let's just do each one after the other. 2 sine of t I minus cosine of t j plus t squared k plus a constant. The constant will in fact be a vector at this point because r is a vector function. You could write c as c1, c2, c3 if you like. Sometimes we will have to find out what the c's are. But now we also said do the definite integral from 0 to pi halves. r of t dt. Well, that is the same as going from 0 to pi halves 2 sine t I minus cosine t j plus t squared k. So we will plug in pi halves, 2 sine pi halves I minus cosine pi halves j plus pi squared over 4 k minus sine of 0 is 0, cosine of 0 is 1, t squared, 0 squared is 0. So this will give us, see, sine of pi halves is 1, so it's 2i. Cosine pi halves is 0, so plus 1j plus pi squared over 4k. That's the answer. All right. Thank you.